Okay. So I was thinking we could start with like quiz 2, looking over how we do that. And then I am in the study room, so the camera's a little wonky. I can like, move it around and stuff. So have it propped up on a chair. Hopefully it doesn't fall. We'll start with number 1. A plane starts from rest and accelerates at a given rate, given by a is equal to that acceleration. From there, we need to derive an expression for velocity. Okay. So I'm going to start by writing that a underneath the word. There doesn't seem to be any black markers, so hopefully these show up fine. You can see that. There's cube t. We can make a note that meters per second cubed times t is going to be meters per second squared once you multiply that t in with seconds. And that comes 2.1 meters over second. So because your acceleration is not constant and it's like a equation for t, then we're going to do the integral. Let me stop the share so that it can record that. Right. So then if we're going to take the integral, remember that the integral is the opposite of the derivative. So the way that I like to remember this is still on the screen. Yeah. So we restart. So you have your acceleration, you have velocity, and then you have your distance or displacement, right? So if you're going downwards from acceleration to velocity to displacement, then you're going like meters per second squared down to meters per second down to meters. So you're kind of like adding a t in my head because to the entire equation, you're adding that value. So then that's when you know you're doing an integral. Integral function, that's what the F stands for. And then probably dt. So then because you use dt, that's the variable you're looking at changing. So it's going to be function of t. In this case, your function of t is your acceleration. Cool. And then if you're going the opposite way, this is something that we did a lot in previous chapters. You go from displacement to velocity to acceleration. Then you're kind of removing a t, right? Because if you have meters over seconds, say to the 6th power, right? And you have t to say the 5th power, that's gonna be 5 over 6, that's gonna be meters over second, right? That's velocity. And if you wanted to go to acceleration, you have to add a t, right? No, sorry, you have to remove a t or second 6. That way that your second at the bottom, one more second stays there than it would have. To the 6th power, that way it's to the 4th power. 6th power is going to be downwards. Six. Right, to the entire equation, you added a t, and that gives you x. That gives you meters, which is x. And then that's doing the derivative of integral. And then if you were to go upwards, you'd be taking the derivative. That's one thing that I don't like about sometimes. She'll be like, derive the expression when you're actually taking the integral or you're plugging it in. So that part can be a little confusing, not gonna lie. But just look at what you need to do and what you're trying to solve for and what you have. All right, so then you have meters per seconds to the 6th power, and then because you removed a t, kind of from the entire equation, meaning that instead of t to the fifth power, you have t to the fourth power. Then your units is going to be meters over second squared. The acceleration. Cool. So then because we're going to acceleration, velocity, then we're going to take the integral, right? Because we want to add a t, like add, so that this becomes t over second squared, and this cancels out to meters over seconds, right? And same here. Oh, this is t squared. You want to add a t there so that becomes meters over second instead of meters over second squared. Then take the integral, you do the opposite of the derivative. So, right, that's integral of a dt is equal to v. And then we're going to do 5. There's a 1 up here. We're going to do plus 1. Oh, let me do this in a color since I can. Plus 1. Take all of that. And instead of going over, we're going under and dividing. So then again, there's a t to the imaginary 0. You're going to add a 1 there. Take all of that and divide it. Cool. And then once you get that, is 5 over 1 plus 1, which is 2, meters over seconds cubed, t to the second place, plus 2.1 over 0 plus 1 meters over seconds, t to the 1. And technically, you should have a constant here, right? Because when you derive any constants that don't have like it starts with a V. Oh my gosh. Variable. There you go. Don't have a variable become 0. So then when you do the opposite, you integrate, you have to add a c. That's usually going to be your v naught in this case, or x naught for x. The problem did not mention an initial velocity, so then you're kind of just assuming from 0. Actually, it says plane start from rest, so you already know that v naught is 0. So you know that's going to be 0. Right? Can you see the blue or the? That's so blurry. I can get a little closer. Okay. Let me just hold this here for a little bit. And feel free to pause it. That's me doing the integral from acceleration down to velocity. Remember that you're doing the opposite of the derivative. So instead of subtracting a 1, you're adding 1, and instead of multiplying, you're dividing. What's most important is that you divide the entire thing that you're adding, so 1 plus 1 or 0 plus 1, over the coefficient. That way, you're actually doing the opposite of derivative. And then that's my little thing that I used to draw on the top of my test. Remember that going from acceleration, velocity to x, you're doing the integral because you're kind of adding a t sort of into the function, just so that if you're going downwards and you're adding a t, that cancels out the second at the bottom by 1 more t, and that gives you like meters per second squared down to meters over seconds down to meters. If you're going up, then you're adding a t so that when you multiply it, that seconds at the bottom doesn't cancel out as much. Right? So you're going from meters to meters over seconds to meters over seconds squared. So that's what that is. Put this back. See if I can get the balance again. Yeah, don't fall. Yeah, if no one showed up yet. If no one shows for the next like time that I have this scheduled, I'll probably just go back to the H402. I also feel bad kicking out like big groups when I'm not in the group. Okay, so then from here, I believe it asks for what's the velocity 2 seconds later. We can do that later. We're just gonna derive the next one for now because we're already on to. So then you know that it's integral. This one's fine. Integral of b dt equals to x, which that means you can. Oh, I should probably see before that. Yeah, I can calculate that. Should actually already have calculated that. Right, so then for our velocity equation, we're just gonna simplify it. 5/2 is what, 25? Yeah. 2.5 meters over seconds cubed. B squared plus 2.1/1 is still 2.1 meters over seconds. T, first power. And then we're gonna do the integral of v dt is equal to x. And then for that, we're gonna do 2 plus 1, take all of that and put it under. 1 plus 1, take all of that and put it under. So that should get us x is equal to 2.5 over 2 plus 1 meters over seconds cubed. T to the third power. See how you added a t, you went from t over squared to t over 3 to t to the power of 3, sorry. And then that cancels out your meters over seconds cubed, which that unit of the coefficient stays the same. Sorry. So that cancels it out. And then we're going to do plus 2.1 over 1 plus 1 meters over seconds t squared. Oh, this is square too. I just haven't written right. Right, and then if we simplify that, then x is equal to 0.83 meters over seconds cubed, t to the third power. Those cancel out to be meters. Then 2.1/2 is 1.05 meters over second squared, t squared, plus c. And we can assume that x naught is 0, so we're going to just do that out. Okay, let me get this close to personal. Okay. Cool, so we should be able to see that. We took the velocity, we simplified it just by dividing, and then you did the t. Then we did the t there, and we put it under. We did the t plus 1, put that all under. I'm gonna just hold it and talk. And then we simplified that down to get our x, right? And we made note that you went from t over t over 2 up to t over 3. So you added a t, and then that cancels out your meters over seconds cubed here, which that's a unit that stayed constant the entire time, right? Cool. I'm gonna go ahead and put this down. And from there, we can plug it in. Because it asks for V of 2. V at 2 seconds, sorry. Once you just plug it in 2.5 meters per second cubed. 2 seconds squared. That's 2.1 meters per second squared. 2 seconds. And then you solve for x at 2 seconds as well. Cool. And then if you plug those in, you should get, I thought, 14.2 meters per second and 10.84 meters. Cool. Oh, before I finish that, the notations that I've been doing over here to the side come from your so when you're doing acceleration velocity, you know the average and stuff, right? You know, v is equal to delta x over delta t, right? Your average of the temperature. Sorry, can we use temperature? So average and then for your acceleration, you also have delta v is equal to over delta t. And then you're going to turn that into the delta becomes a dv over dt, right? So we can kind of assume that v so x naught is equal to 0 meters and v naught is equal to 0 meters or seconds. So then that means that delta v delta x, right? So it's just the same. Then we have v is equal to x over dt. You get that over there. So v dt is equal to x. And then you get this v over dt. Multiply it over. A dt equals to v. And then you're going to add the equal sign so you can get rid of that dt or dt on this. Cool. So is this here the derivative form? And this here's the integral form. If you do have if you do have a x naught or v naught that is not 0, then you still kind of do this, but when you do the integral, you evaluate it at the final and initial value. So then when you get your equation, you do this like little bar, so you have final, initial, So then you do f at final minus f at initial. And then that's how you handle the integral if you have like multiple variables, and you cannot see much of that out. Okay. Start here with me. Okay. So right, that's us plugging it in. We got 2 seconds and I got 2 seconds. You just plug it into the equation, plug that into your calculator, and you get the values. If my values are incorrect, I kind of did the calculator plug-in in a rush, so that's probably why. As long as your equation was kind of the same, we got those with by they're integrating the acceleration. And then from there, I'm showing you how I know what the integration is, kind of. Because you know that velocity is delta x over delta t, which is the same for your average velocity. But then for instantaneous velocity, I think the book tells you you're taking the limit of. The easier way to do that is to do the dx over dt version and then take the integral. So then I'm saying you can assume x naught is equal to 0 meters or v naught is equal to 0 meters. Just because that's what makes sense in my head to get the integral form. But technically that's just the integral form and you just memorize that. And then, for the integral, you're kind of solving it at the final and the initial. So then that would be your notation. You have your equation, and at the end of the equation, you have a line with your, say, t final, t initial. And then it would be like f, the function at that final value minus the function at the initial value. I don't actually remember her doing anything that required you to do final initial, but I have done it a bit. So I just wanted to share it in case it was from this class. So yeah, that's how I know which one it is to integrate. Oh, it's back here. Okay, that works. So I'm gonna go ahead and share my screen. Well, so that's kind of what she did here. She showed you that it's like integral. Also, see, she does include the final. That's v final, and that's your v initial, t final, t initial, right? And here she's saying like v naught is 0, so that one's gonna be v minus v naught, which is v. So then you integrate, and then you do this integral. Again, your x naught is 0, so then that side becomes 0. And then you plug it in. And the second one asks for a dolphin jumping up. So go ahead and look it up while I erase the whiteboard. Funny, whenever I use whiteboard in public spaces, I'm always tempted to just leave it there and let people wonder what we were doing. Okay. The dolphin can jump straight up to the height of 2 meters. What's its initial speed and how much time is it in the air? So you're assuming the dolphin is jumping out of the water. Then that's flat. Right? You're ignoring any little height difference in the waves. Why are you going to calculate that? So then you have its total height, or max height, sorry, at 2 meters. And then because this is like you're approaching it like a free fall problem, right? So this is V naught. And then this coming down over here is symmetrical, so V is equal to negative V naught. I'll put the final. Alright, up here at this top, you know that V is equal to 0. I'll put V top. And then that's also your max height, which is what they told you. And then you also know that it takes the same amount of time to get up and the same amount of time to get down. So T1. And then here it's 2 T1 is T2. And then this is T naught, which we're assuming is equal to 0. Okay. Let me grab the camera and show. Oh, I should probably stop sharing and pin the video. There we go. You pull the camera closer. There we go. All right, so you have your V naught, and then you have your max height, where you know your V is equal to 0, and then you have your final velocity and your final time. You know it takes the same amount of time to get to the top of the jump as it takes to get to the bottom of the jump. Cool. So then the first thing it asks for is its initial speed. All right, so here we can use a kinematic equation. The question is which one? Well, what we have is really just the max height. But we also have that at the max height, our velocity is equal to 0 meters over seconds. But we also know that the only acceleration here is gravity, because it doesn't mention another acceleration, and that's a free fall problem. Cool. So then we can probably use the V is equal to V naught plus V squared is equal to V naught squared plus A delta X. Right? Because we have the delta X, and we technically have X naught, which is 0 meters, right? So let me expand that delta X. X minus X naught. This one we have, we're going to do that at the top. This one at the top we have. We're solving for this one. We have acceleration, right? This X naught is 0 meters. This XT is 2 meters. And acceleration is gravity. It's negative gravity since we're just finding a positive axis as upwards. We're solving for that one. And then we have the top, which is 0 meters per second, right? So then we can either plug it in straight and solve it from there, or I like to do it with symbols first. So we're just gonna move the A delta X over. So that's gonna be T squared equal to minus negative G, because we can plug in the acceleration. It's already a symbol until we plug in the number. Let's write delta x for now. Delta x is equal to v naught squared. And then we can take the square root to get rid of that squared on the v naughts. Cool. So then that gives us the equation v naught is equal to the square root of the t squared plus, because the minus a negative is equal to gravity delta x. And there we go, just plug it in. This is going to be 0 meters over second squared plus 9.8 meters over second squared times 2 meters minus 0 meters. Which that is equal to, I'll do it below. 28 times 98 times 2. Oh, shoot, I forgot a coefficient here. There's a 2 in front of this A. So, 2 times 2. So then that's going to be 4 times 4 meters times 9.8 meters over second squared, which is equal to not a 9, that is a 4, which is equal to 6.26 meters over second. So V naught is equal to 6.26 meters over second. And then because we solved for that, we can plug that in, or we can write it into our little diagram. You don't always have to write the diagram unless she says like, show, fill this. But I like to write it just because it helps me keep track of everything. And then from there, it asks how much time is it in the air. So we don't have any time in this one, but now we have V naught. So that leaves us with using either one of the 2 other ones. We have the V is equal to V naught. Oh, I should probably ask you. If you guys see this better. There we go. All right, we have max height, we have V at the top, we have acceleration. That's the kinematic equation where we only have one unsolved variable, which is what we're solving for. Because remember, you can only solve for one variable with one equation. That's why sometimes we'll do substitution, because we have 2 variables. And so then I symbolically isolated the V naught. Also plugging in acceleration as negative g because I can. Then that's the equation that I got. And then I plugged it in, simplified, and then got the V naught. So there you go. Okay. So we're solving for time. I would honestly use the V equation over the X equation. The X is equal to X naught plus V naught T plus 1 over 2 T, 1 over 2 AT squared would work. You have all of them, but in my opinion, the V is equal to V naught plus AT is faster because there's less variables to work with. So, let me use label. This is part A. So we're going to do V naught AT. Let's double check that we have everything. We have V now, yes. That's VT. We have V naught, yes. We have acceleration. Acceleration is negative g. V naught is 0 meters over second. VT is 6.26 meters over second. And T we're solving for. Cool. So then let's isolate T. We can do that by doing VT minus V naught equal to AT. Divide both by A. Right? I'll just plug in A for as negative G. Oh wait. So A is equal to negative G. So T is equal to VT minus V naught over A. Remember that this is one of the ways that we derive this kinematics equation. Because you know that A is equal to delta V over delta T. So then that means that A delta T equal to delta V. You assume T naught is equal to 0, so then that gives you A T is equal to V minus V naught. To get rid of the negative, you move V naught over, so V naught. That's something that we should have already learned from previous classes. Anyway, I digress. We plug in for T. 0 meters over second. I mean, keep my color consistent. So those two cancel out because that 0 is basically nothing. For units, you have meters over seconds, meters over second squared. You can do my way where you multiply them both out like that. Squared, meter seconds. Those cancel out, which gives you seconds. Or you can do the other way, which you're gonna just take the inverse of 1. So meters over second times second squared over meter. Those cancel out, which gives you seconds. Either one is fine. The brackets just makes more sense in my head. It doesn't mean it has to make more sense in your head. Anyway, digress, we solve for T. And we get 0.64 seconds. But wait, we're not done yet. That's to reach top. Reach the top. And then we have to remember that T final is equal to 2T at the top. So T final is equal to 2 times 0.64 seconds. So T final is equal to, I got about 1.3 seconds. And since we got that, we can go ahead and put that into the drawing. Because why not? Two 0.64 seconds. Okay. Let me move the camera so you guys can see it. Okay. So we checked that this equation, we have everything we need. We isolate for the variable we're solving for, which is T. Right? From there, we come back over here, we put things in, cancel stuff out, because those negatives are going to be coming positive. If you ever have negative t, by the way, something is wrong. You shouldn't have negative t, because you can't go backwards in space. And then you get 0.64 seconds, but that's to reach the top, right? Because we use v final as the v0 at the very top. If you didn't want to do this, you could technically do like v final is negative 6.26 because you know that v naught is equal to negative v final, but then you get like a 0 at the top and you wouldn't get a useful answer. So that's why we do it this way. And then we know that it takes same amount of time to get to the top as it takes to get it down. That means the total time is the time to get to the top times 2 or plus. So I do times 2 right there times 2. That gives us 1.35 seconds. This down here is just me checking the units with this meters over second squared. This is how I like to do it with the brackets. And then the outer combined with the inner, and then you count up from there. Another way you can do it is you do the inverse of one of them and you count up from there. And then that over there is just a reminder that we derived this kinematic equation from the average acceleration equation. Where you have like A is equal to V delta V over delta T. You assume delta T0 is equal to 0, so then you have AT is equal to V minus V naught, and then you just get rid of the negative by moving the V naught over. And that is quiz 2.